everyone. Good afternoon, everyone, and welcome back. Today, we are going to continue with our review of the operating system support. Okay, you remember last week we talked about this operating system support. Okay, last week we were talking about how the Cortex-M processor supports operating systems. Right, the Cortex-M processor architecture has some features that support operating systems. So last week we talked about the control stack and sysdig, right? So today we are going to finish off our discussion by looking at this memory protection unit, SVC, and Pendable supervisor call. This MPU, SVC, and Pendable supervisor call. So we're going to look at these three things today, right? But before that, let me take your attendance first. Right, Brenda. Okay, good afternoon. Chen Supian, right? Chia Chai Siu, Chu Zhang Hing, Chua Yu Yang, Ernest, Go Kian Sing, Hu Hing Dong, Hu Hing Dong, Gu Bun Kiong, Lau Lok Jing, Li Zilim, okay. Lim Chun Wei, right? Lim Wen Yang, Lim Yong Chuan, okay. Long Yao Ting, good afternoon. Lo Tiong Lia, okay. Lu Jui Min, Ng Han Xiang, Ng Wei Hong, Ong Mei Lin, Hong Shui Wen. Oh, yeah, Lao Lok Jing is here, thank you. Hong Shui Wen, Hua Yi Hang, So Yan Cheng, right? Tan Xin Shen, Teo Liang Ho, Teo Yi Si, okay. Hua Yi Hang is here, okay. Wong Chung Yi, Wong Ka Sing, right? Yong Wing Liang, okay. Yong Chi Ye, good afternoon. Okay, let me check again. Chu Zhang Hing, are you here? Chu Zhang Hing, Lim Wen Yang, Hong Shui Wen, Tan Xin Shen, Teo Leong Ho, okay, Teo Leong Ho is here. Wong Chung Yi, okay. I'll check your attendance again later. All right, so let's start our discussion with continuing from where we left off last week. Yeah, okay, thank you. So last week we talked about the control register. Okay, you know the control register got two bits. One bit to select privilege, another bit to select the stack pointer. Okay, why privilege? Because operating system code has privilege, thread code no privilege for security lah, for reliability lah. Stack pointer, we got two stack, main stack and process stack. Operating code use main stack, thread code use process stack. I separate so that you have security. Thread code cannot simply access the memory of the operating system code security. So that's why we separate. So now you understand the control register and the two stacks. Okay, so then all operating system activity, all your operating system activity are based on the sysdig timer interrupt. Okay, so the sysdig timer, you can program it's when you want it to interrupt. So the default value is 1 millisecond. So every 1 millisecond, the sysdig timer will generate an interrupt. Okay, every 1 millisecond, sysdig timer will generate an interrupt. And what happens is so every 1 second, the sysdig timer generates an interrupt. And whenever the sysdig timer generates an interrupt, the operating system code will run. All right, the operating system code will run. The operating system system code to switch to another thread. Okay, so here you got your sysdig. So here is your thread code. Okay, we got thread 2, thread 1, thread 3, and thread 4. So thread 2 is running, thread 2 is running. Then the sysdig timer, the sysdig interrupt happens. So the sysdig handler will run. The sysdig handler will then run the operating system code, which will then switch to the next thread 1. Okay, so thread 1 runs until the next time slice, sysdig goes off again, then we switch to thread 2. Okay, now thread 2, you notice here thread 2, it calls SVC, supervisor call. Why? Because threads, right? Threads, they do not have privileged access. So threads, they cannot access the operating system data. What is operating system data? Example, semaphore or signals. So you see here, thread 3 has higher priority than thread 2 and thread 1. But why isn't thread 3 running? Probably because thread 3 is waiting for maybe a semaphore or a signal or a message. Okay, so thread 2 signals thread 3 to run, or thread 2 releases the semaphore that thread 3 is waiting for, or thread 2 sends a message to thread 3. Whichever it is, all these are operating system objects. Signals, semaphores, message queues, they are operating system objects. So the thread cannot access operating system objects because it got no privilege. So how does code with no privilege access memory data that requires privilege? How? This is why we have supervisor call. This is why we have the supervisor call. The supervisor call is actually a software triggered interrupt. It's a software triggered interrupt. Normally, you study interrupts, or interrupts are triggered by hardware. That means the timer, when it overflow, it generates an interrupt, or when the timer underflow, it generates an interrupt. If it's a GPIO interrupt, so your GPIO pin is connected to something, when that something has a logic state change, 0 to 1 or 1 to 0, then you detect it and generate an interrupt. All of these are known as hardware interrupts. Some physical event causes the interrupt to be generated. Some physical event. These are hardware interrupts. Now we also have software interrupts. Software interrupt is the interrupt is triggered by software code. For example, your thread 2 is running, it got no privilege, but it needs to send a message to the message queue. The message, if you want to put a message into the message queue, the message queue is a operating system object. You need privilege. So the thread don't have privilege. What the thread does is it will trigger a software interrupt. When the thread triggers a software interrupt, the processor will then run the interrupt handler. So the software interrupt is the supervisor call. Okay, this is the supervisor call exception is a software interrupt. So when the thread triggers the supervisor call exception or interrupt, supervisor call exception, so then the supervisor call handler will run. And exception handlers, when exception handlers run, they always have priority. Okay, when exception handlers run, they always have priority. So the thread don't access the privileged object by itself. The thread asks the exception handler to do it for the thread. Okay, so the thread triggers the SVC exception, then the SVC handler will run, and the SVC handler will then do the things that requires privilege for the thread. Okay, so what's the advantage of this? You see, what's the advantage of this? You see, let's say you have there is a kitchen. Let's say there is a kitchen. Inside the kitchen, there is lots of food. Okay, you can make pizza, you can make pancake, you can make burger, whatever. Right? So you are the customer. Are you supposed to go into the kitchen and make your own burger? You don't, right? It's dangerous, because the customer's hands might have germs and virus. They don't know what the customer will do when they go into the kitchen. So we don't let the customer go into the kitchen, right? We have the professional cook standing there in the kitchen. So the customer tell the professional cook, I want a burger. Then the professional cook will then take the ingredients from the kitchen and make the burger. So the SVC handler is like the cook. The cook deals with the raw materials in the kitchen for you. You just tell the cook what you want, right? You don't simply go into the kitchen and make a mess of everything there, right? And you see, when you tell the cook what you want, the cook will do it in a very defined way, right? It's all defined. Now, this is the supervisor call. The supervisor call is, which is it? Wait, let me go to the supervisor call. There it is. So the supervisor call exception, the supervisor call exception, the SVC exception, right, allows your application, this is your user code, your user thread code. Okay, it allows your user thread code to access the services of the operating system. What are the services of the operating system? Signals, semaphores, message queues, memory pool, mail queue, all those stuff are services, or peripheral hardware. So all these things, these sensitive resources, we don't let the user thread, the user code, access them directly, right? We protect them. We protect them using the operating system. So the operating system is your middleman. You don't, your user code, you don't access those things directly. If you want to access them, you go through the operating system, the middleman. Okay, so all these services, these peripheral hardware, these are like all the stuff inside the kitchen, right? You don't go inside and mess with them. You tell the cook, the operating system, what you want, and then the cook will do it for you. Okay, so what's the advantage of this? The advantage is security, because when you tell the operating system what you want, how you do it, you trigger SVC. So SVC has a parameter one. You remember in week 4 you learn about the SVC. SVC has parameter. So the parameter for SVC is a number between 0 to 255. So when you trigger the SVC exception, you provide a number between 0 to 255. That means you're telling the operating system which particular thing you want it to do, right? And there are 256 different options. So you see, it's well defined, is limited, is fixed. The scope is fixed. You can only tell the operating system to do 256 different operations. It's all fixed. Okay, so it's like you tell the cook, I want burger, I want pizza, I want fries. You don't have a burger pizza or a fries burger. You know all this weird stuff. You cannot do it. Okay, because the things on the menu is fixed. The thing on the SVC menu is fixed, only 256. So it's safe this way. The application cannot simply access all these things and mess up. Okay, application have to, through the SVC exception, tell the operating system what to do, and the operating system will carry out the operation. Okay, so that's what SVC is, a supervisor call. You see, uh, the supervisor call is exception number 11. Exception number 11. You got another supervisor call. It's called the pendable supervisor call. Pendable supervisor. What's the difference? Supervisor, the execution is precise. Precise meaning that when you execute the SVC instruction, right? When you execute the SVC instruction, you will trigger the SVC exception to run immediately. It must run immediately. After the SVC exception, right? The SVC handler must run immediately. If not, you will have a fault. A fault will be triggered. It's an error condition if it cannot run immediately, right? Now, pendable supervisor call, the execution is not precise. It can be delayed because interrupts. If your interrupt is not the highest priority, right, you trigger it, it won't immediately run. You have to wait until all the other higher priority interrupts get service, then only this interrupt gets to run. Okay, so the execution is not precise, can be deferred. So we have two different applications. There are certain things, when you trigger, you need it to run immediately. Those are SVC. There are certain activities where when you trigger, you don't need it to run immediately. You delay until all the other more important interrupts get service first. So for those things, we use the pendable supervisor call. So this guy is exception number 11. Pendable supervisor call is exception number 14. Your system timer is exception number 15. So you have a total of exception number 0 to 15. You have a total of 16 system exceptions. These are the interrupts generated within the processor call, system exceptions. Number 16, 17, 18, and so on, those are microcontroller parallel interrupts. Okay. Exception number 0 to 15 are interrupts generated from inside the processor call. You call these system exceptions. Exception number 16 onwards, all of those are microcontroller peripheral interrupts, right? Okay, so SVC, is triggered by the supervisor SVC instruction, and pen SV is triggered by the pen SV pending bit. Okay, you remember you studied the system control block on week 5, the system control block. So the system control block has the interrupt control and state register, ICSR. ICSR bit 28, ICSR bit 28, the pending status bit for pen SV, dependable supervisor call. Okay, so if you set this bit, you will pend, you will trigger a pen SV exception. Right? It's like the interrupt flag. When you set the interrupt flag, you are basically triggering that interrupt. So these two are what we call software interrupts, because you see they don't come from hardware. It is the code that generates this interrupt. Your user code, you execute the SVC instruction, or you go and set this bit, you will trigger an interrupt. Okay, but you notice that this the SVC instruction cannot be executed by thread code one. So if you refer to your lecture week 4 notes, you have to define certain functions as SVC function. Okay, you have to make a particular function an SVC function. So when you execute that function, you will trigger the SVC exception. Okay, and NSE cannot be triggered by thread code because the system control block requires privilege to access. So PanSV is not used by threads one. PanSV has a very special purpose. It is used for context switching. I will talk about this shortly. The usage of PanSV for context switching. Now we come back to SVC first. So you understand what SVC is already. SVC allows user code to access hardware. Okay. All right. Let's go back to the sysdig just now. So over here, uh, your thread 2, just now we're talking about thread 2. So thread 2 uh, calls an SVC function, which is probably to release OS semaphore release or OS signal set or OS message put. You are basically making some resource that thread 3 is waiting for available. So immediately thread 3 will get to run. So after the SVC, immediately you switch to thread 3 because thread 3 has higher priority. Okay, and the thing that it is waiting for has been released by thread 2. So thread 3 preempted thread 2. You notice? Thread 2 has been preempted by thread 3. So thread 3 gets to run right until the next system tick. So during the next system tick, the system tick, the task manager will check who is the highest priority thread. It's still thread, so it goes back to thread 3. Thread 3 needs to run until the next system tick. Now you notice during this system tick, right, an interrupt happens. So this ISR, this is a microcontroller peripheral interrupt. It can be a GPIO interrupt, can be an ADC interrupt, can be a timer interrupt, anything. Your microcontroller peripheral interrupt. Okay, so this interrupt happens. You notice that it is disturbing your sysdig. It preempted your sysdig. Now this is very dangerous. Why is it dangerous? Because if this ISR is not short, it is long. If this ISR code, you go and put a lot of stuff inside, it's very long. What happens is, if it continues running, then sysdig cannot finish within the current system tick, and it doesn't trigger in the next system tick, then your operating system timing will be all wrong already. Okay, it's like the sysdig needs to run once every, let's say, once every 1 millisecond. So the sysdig needs to run once every 1 millisecond. But if your ISR code is so long, you are obstructing the next sysdig from running, then the operating system timing will be wrong already. Okay, so that is why we keep our ISR code as short as possible. We don't put the processing inside the ISR. The ISR we just signal. We just use a signal. We signal a high priority thread to run. So in this example, it will be thread 4. You notice here, thread 4, right? is where we put the code of the ISR. So the ISR code, we take it out, we put it inside thread 4. And then when the interrupt happens, the ISR just triggers. It just signals thread 4 to run. So thread 4 is waiting for the signal. Right? Thread 4 is waiting for a signal. But the ISR, it doesn't switch to thread 4 immediately. You notice the ISR will go back to the sysdig. So the sysdig gets to finish. This is very important. The sysdig must finish before the next sysdig happens. So the operating system timing is okay. Right? So this is where we use the dependable supervisor call. The context switching, the code to switch to another thread, the code to switch to other threads, you put it inside the dependable supervisor call. Why? Because the dependable supervisor call is normally given the lowest priority. So it will only run after all the other exception handlers has finished. In this case, after sysdig has finished. So after sysdig has finished already, there are no more interrupts. So the dependable supervisor call will run, and then it will switch to thread 4. Right? So you avoided disturbing the sysdig. Okay? If the ISR immediately you switch to thread 4, then the sysdig handler cannot finish, right? That's dangerous. So the ISR returns back to the sysdig, let the sysdig finish. Then the dependable supervisor call is where you put the thread switching code, the code to switch threads. Then you switch to thread 4. Right? Sysdig runs again. Thread 4 is still highest priority, haven't finished yet, so thread 4 finishes running. Now, thread 4, you see here, thread 4 is probably uh, triggering. This is SVC. So thread 4 is releasing something that thread 3 is waiting for. So that's why thread 3 runs again. Thread 3 runs again. Okay. And then thread 3 finish already. Thread 3 finish already. So you go back and resume back with all those lower priority threads. So this example is just to show you that you can see from here, the operating system code is all placed inside 3 exception handlers: the sysdig exception handler, the SVC exception handler, and the PAN-SV exception handler. Okay, this is why your operating system will always have privilege, because your operating system code is entirely placed inside these 3 exception handlers, and exception handlers always have privilege. Okay, because exception handlers always have privilege, you place the operating system code inside these 3 exception handlers. So the operating system code will always have privilege. Okay, right. Now, the next thing that I want to talk about is the memory protection unit. I want to talk about the memory protection unit. So you see, the memory protection unit, you remember on week 5, the memory protection unit is to restrict access to certain parts of memory. You want to restrict access to certain parts of memory. Okay. So actually, what how the MPU is supposed to be used is how the MPU is supposed to be used is, okay, this is for example your memory. This is for example your memory. So your memory, as you know lah, got 6 regions. The bottommost region, this is the code region. This is to store code. This is to store code. Okay, code is read only. Code cannot be modified on. So we are not concerned with code. What we are concerned with is the data region. Because data is read write. This is your SRAM. Your SRAM is read write. So it's dangerous. Okay, it's dangerous because what if one thread go and access the memory of another thread and modify it? What if one thread accesses the memory of another thread and modify it? So this is your data. Okay, this is your data. Okay, now you see, let's say this part here, this part of your data memory is the main stack. This is the main stack. This is the OS data used by the operating system. Then here you have another part of memory. This is the process stack. This is the process stack for, let's say, thread 1. So all the data used by thread 1 is put here. And then maybe here, just give you an example. This is the process stack for thread 2, thread 2. So all the data used by thread 2 is placed here. Now, ideally what we want is when thread 2 is running, right? When thread 2 is running, only this part of memory can be accessed. Everything else cannot be accessed. Everything else cannot be accessed, right? So we can use the memory protection unit to do this. We can use the memory protection unit to do this. We can we can define you know your MPU, right? How you define MPU region? You provide the base address, right? Then you provide the size, right? Then you provide the attributes for this region. So remember how you program your MPU? You set the base address, you define the size, and then you define the attributes for this region. So, and everything else undefined. So what happens is when your thread is running or thread 2 is running, it can only access this part of memory. If it tries to access anything else, you will trigger a memory fault, memory management fault. So that's how you restrict access. But this mechanism is only provided by, for example, it's provided in other operating systems. For example, FreeRTOS. But now, FreeRTOS is not a topic of this our syllabus. So I provide some code, some example here to show you how the MPU is used with FreeRTOS, and you can go through this code. Okay, you can. There's quite a lot here. Uh, MPU support with FreeRTOS. You can go through this. It explains how FreeRTOS provide you with memory protection unit support, so that you can do this. You can do this. Okay. This is not provided by Kale. We have a lot of RTOS. FreeRTOS is very popular because it's free. It's open source, is free. But it is because it's powerful, so it's relatively very complex. It's really complex. So I use RTX to teach you because number one, RTX is also free. Number two, RTX comes with microvision. And number three, RTX is much simpler than FreeRTOS. But you know lah, when it's simple, you don't have so much features. So RTX don't have MPU support one. So if you want to use the memory protection unit with the RTX, how can you use it? Well, what it says here is, I just draw it out. What it says here is, how we can use it is we use it to detect stack overflow. Okay, so let's say this is thread. This is your thread stack. This is your thread stack. So your process stack pointer is pointing here. This is address going up, and this is memory. So address going up. So your stack pointer is pointing here. So when you put things into the stack will grow downwards. Grow downwards when used. Okay, your stack will grow downwards when it's used. Now, it's very dangerous. It's dangerous because one of the most common errors is stack overflow. Because you see, you have a finite size. Your stack has a limited size. If you keep pushing things into the stack, very easy you can get stack overflow. For example, now your RTX or your thread stack is 200 bytes. You only got 200 bytes. If you know what the stack is for, the stack is used to store local variables. The stack is used to store local variables. So what if you go and create something like this in your local variable, you know, your thread void thread a void, for example lah. This is your thread now. You go and declare here, int. You go and declare an array with 100. You got stack overflow already. You don't realize it, right? But you see, when you create an array with 100 members, it's type integer. Integer is 4 bytes. Integer is 4 bytes. 32 bits, 4 bytes. So 100 members, this will be 400 bytes already. 400 bytes way exceed your default thread stack size of 200 bytes, right? So you see, very easy you can exceed one. And this is just a simple example. There's a lot of ways that you can accidentally produce stack overflow. And it's not easy to identify. In fact, some of the cases are very difficult to debug one, to find out one. So The thing is, what happens when you get Stack Overflow? When you get Stack Overflow, your programmer will start to do very weird, unpredictable things, and that is very, very dangerous. Our program will run out of control when you go Stack Overflow. If your thread stack, you exit, you go here already, you may be writing into the memory of another thread. That's dangerous. Now, when you use RTX, you don't know there is Stack Overflow until you switch to another thread. So let's say currently you are running this thread. Stack Overflow happens. The program starts to go out of control. You wouldn't know until until the task manager run and switch to the next thread. When the task manager run, it will check for Stack Overflow. Then only it will detect the Stack Overflow. So this is very dangerous. Do we have a solution where we can detect Stack Overflow happening the moment that it happens? Yes, we can. There's one thing we can do. What we can do is we can declare here at the bottom here, at the bottom of your thread stack, right at the bottom here, we can declare here MPU region. So I can set the base address. I set the base address, and then the size, you just set to the smallest size, 32 bytes. So the smallest MPU region is 32 bytes. Okay, and then you just set the attribute, set the attribute to no access, no read, no write, nothing. Nobody can access. So when you push things into the stack or you use the stack, the moment the stack writes into or reads or writes into this no access region, you will immediately trigger a memory management fault. The processor will immediately stop running and then go to the fault handler. Right? This way, you prevent the program going out of control. Right? You detect the Stack Overflow happening the moment that it happens. So this method, we call this method electric fence. You notice this like, we call this the electric fence. Electric fence. So it's like you're putting up an electric fence here. The moment the processor tries to go past, you get electrocuted. Basically, you go to the fault handler. Everything stopped. You go to the fault handler. Okay. So this one, you have to do it yourself. You have to manually code this. You have to manually set the uh, an accept a memory an MPU region with no access, smaller size, and you have to set below your thread stack. Okay, you have to manually set this because RTX doesn't provide MPU support. Okay, so this one way that it can be done. Right. Okay, so that's all about the MPU. Basically, we use the MPU for normally the MPU is used like this, but RTX don't support. So what we can do in RTX is a very limited use of the MPU. We use it like this just to prevent stack overflow, which is very important. Stack overflow always happen. I guarantee you that when you do your assignment too, you definitely get stack overflow. But it's a good thing. When we make errors and we solve the errors we understand the thing better. And as engineers, we will have errors 100%. Right? That's where our job is not to design things that run perfectly. Our job is actually to fix errors. Right? When we design things 100%, you will get error one, big or small, you definitely get. Our job is to understand the error and fix it. Okay, and actually our job is to continuously fix errors until we run out of time. You can never totally remove bugs unless the program is really too simple. Okay, okay. Um, all right, now we go to the next one, which is we talked about MPU already. So just now we also talked about the SVC already. So we go on to the last one, which is the Panasonic. Panasonic is a very, very long story. Pendable Supervisor Call is a very long story. Okay, let's start this very long story. Let's start this very long story. Now, just now I was telling you about operating system code is placed inside sysdig. Okay, operating system code is placed inside sysdig. So when the sysdig handler runs, you switch. So task A is running. At the end of its time slot, operating system code runs. Switch to task B. Task B runs until the end of its time slot. Operating system code runs. Switch to tasks A and so on. Okay, so this is fine. This is very simple. This is fine. But we have a problem. The problem is when interrupts happen. Okay, you see, when interrupts happen, right? when interrupts happen. So your operating system sysdig handler runs, operating system code runs, switch to task A. Then at this point here, right, an interrupt happens. So the interrupt handler starts to run. The interrupt handler starts to run. Now, until here, the interrupt handler hasn't finished yet. The next sysdig happens. So then the operating system code run. The operating system code runs, and then it switches to task B. Notice that interrupt handler has been paused. Cannot happen, right? This should not happen, right? When an interrupt happens, the interrupt handler should run and finish as fast as possible, right? But now it's being delayed. Task B runs until its time slot ends, switch back to operating system. Operating system code then resumes the interrupt. So your interrupt processing has been super delayed, right? So what is one thing that we can do? One possible solution, right, is we we don't carry out the context switching, we delay the context switching. So you see here, task A, okay, context switch to task B, context switch to task C. Okay, IRQ happens, intro happens. So the intro happens, then your operating system code run, right? But to avoid delaying the interrupt handler, we don't do context switching. So after the operating system code runs, we don't do context switching. You can continue back and finish your interrupt handler. Okay, fine. So our interrupt handler okay already, right? No, not delayed already lah. But you see what's the problem? We didn't context switch. So after this IRQ done, you see task C continues running. You only go to task A on the next system tick. So what's the problem? The problem is if your interrupt happens very frequently. If your interrupt happens very frequently, you see, if the interrupt is generated periodically, very frequently, and it coincides with your task switching activities, right? That means your interrupt keeps getting generated now. Then now you keep delaying your context switching. So task C will run forever. A and B will never get to run. Okay, the context switching may not be carried out for a very long time if the interrupt happens too frequently. So is there a better way to do this? Yes, there is. What we do is we create a special interrupt handler with the lowest priority. We put context switching code there. We create an additional interrupt. Not we, this is what the ARM Cortex M system designers that did. They created a new interrupt. They call it the Pendable Supervisor Call interrupt. And this interrupt, normal usage is we give it the lowest priority. So what do we do with this interrupt with the lowest priority? We put the context switching code inside this handler. So context switching will happen when all the other interrupts have been serviced. Okay, so like this. Now, task A run, right? Then your sysdig handler run. But now the context switching code is not inside the sysdig handler anymore. We move the context switching code to PanSV. So what the sysdig handler does is it will trigger PanSV. So when the sysdig handler runs here, it triggers PanSV. So then after the sysdig handler finish, no more interrupts already, PanSV runs because it's the lowest priority interrupt. So it runs and then it does the context switching because it has been triggered by the sysdig. So PanSV runs, does the context switching, so we switch to task B. Okay, fine. Then on the next system tick, operating system code runs, then it will trigger the PanSV to run. Okay, once the sysdig finish, PanSV will run. PanSV will do context switching to task C. Okay, task C runs, and then here you see the interrupt happens. The interrupt happens, so the operating system code will still run. The operating system code then triggers context switching. But the IRQ can continue and finish because the IRQ has higher priority than PanSV. So you'll continue until finish. Then only PanSV runs. And then PanSV will switch to task A. So you see, we still get to switch. And but now the context switching code will only run when there is no other interrupts or exceptions uh, anymore. All fully serviced already, then only the NSV will run, lowest priority. So context in other words, context switching happens when all other interrupts have been serviced. So you don't delay the execution, the response to interrupts or exceptions. Okay, so this is the purpose of the PanSV handler. Now, so the PanSV handler is specifically used for context switching, right? PanSV handler is specifically used for context switching. Let's look at some code. I want to show you some code here. Okay, I want to show you this program. Now, this programmer, this page, page 14, this programmer is this is the basic principle of an RTOS. If you want to write your own operating system code, this is the basic version of an operating system code. Because an operating system, the basic job is to switch between threads so that you can have multiple threads running at the same time. Looks like they're running at the same time, but actually they are being switched very fast. This is the premise of a real-time operating system running on a microcontroller, right? With a single processor. You're actually sharing the processor between multiple threads so that they look like they're running at the same time. The basic mechanism is the thread switching mechanism. And the thread switching mechanism is done in the PanSV handler. So what do we mean by thread switching? Now, the idea of thread switching is this. This is the idea of thread switching. You see, yeah, this is memory. So down here is your code lah, right? Up here, this is your data lah. This is your data region, this is your code region. Okay, this is your code region, and this is your data region, right? So let's say here, this is the thread one code, okay? And then this is the this is the thread one stack. Okay. Then we got this is thread two code. It's just sitting somewhere inside your memory lah. Okay. And then this is the thread two stack. Okay. So then this is your CPU registers. So these are your CPU registers. So your CPU registers, you know lah, you got R0, R1, R2, all the way until R15, and then you got your XPSR, program status register. Okay, so you see, when your program is here, when you are running here, when you are running track 1, when you are running track 1, when you are running track 1, the CPU registers will be holding the values being used by track 1. Okay? When you're running track 1, the CPU registers will be holding the values, the R0 to R15 and the program status register values used by track 1. Okay? All right. Now, when you want to switch to track 2, what do you do? When you want to switch to track 2, you have to when you want to switch to track 2, you have to copy everything here, copy it into the track 1 stack. You have to save it here. Save it here. Okay, you have to save it here. So how many do we have? We got 16 registers here. R0 to R15. We got 16 registers here plus XPSR. Okay, so you have to save everything here into the track 1 stack. Okay, so this number one, you have to save everything here into the track 1 stack, right? Then number 2 is you have to take the CPU register values used by track 2, right? And then you load it into the CPU registers. Then you can now run track 2. Okay, so now you're running track 2 because the thread 2, its registers have been loaded inside already. Now you can run thread 2. So you run thread 2, run. Okay, until thread 2, the time slice is over. Now you have to go back to thread 1. So what happens? If you have to go back to thread 1, then everything here, you have to save it back inside. 3, you have to save it back inside. And then you have to load this one, number 4. You have to load it back. So now the CPU registers will have the values of thread 1. And then you can continue running thread 1, right? So this is known as the thread context. The thread context. It's like, it's like, let's say, your class got 30 of you, let's say, just a analogy, right? There's 30 of you in your class, 30 of you, but there is only one body. So all 30 of you, you're all spirits. You're all spirits. There is only one body. So each of you can only occupy the body for maybe 10 minutes. You have to take turns. All 30 of you, you have to take turns to live in the physical world. So each of you only have 10 minutes to do it. So when it's your turn, so all your thoughts, your memories, everything will be downloaded into the body. And then you start to live your life for 10 minutes. At the end of your 10 minutes, you have to take all your memories, everything, you save it, and then you go into a hibernation state. You wait until all 29 others finish already, then it's back to your turn. Then you can load all your memories back into the body, and then you continue your life for another 10 minutes. And then your 10 minutes up already, then you have to go into hibernation state again, wait until the other 29 has lived their lives, then you continue again. So this is the life of a computer programmer. Very miserable. They have to share the operating system. Okay. So and this is what happens here. So let's look at this program now. Let's look at this program. Let's look at this program. Uh, it's a bit technical, so I hope that you go and study this after the class, right? You go and study this after the class. It's a bit technical, because why I say technical, you need to understand everything that we've been talking about for the last 10 weeks, right? Okay, so let's start here. Now, we have 4 tasks. We have 4 tasks. 4 tasks. We're going to run 4 tasks at the same time using an operating system. So what are those 4 tasks like? Okay, let's see. Now here, these are the function prototypes. These are the function prototypes. So you got task 0, task 1, task 2, task 3. 4 tasks. So the task is over here. Yeah, the task is over here. Right? It's a very simple task. So task 0, you turn on an LED for a certain delay. This is a delay loop. Then you turn off the LED for a certain delay. So you notice we got some LED functions here. Don't bother about them. Don't bother about these LED functions because, okay, you see here, the LED and the UART, the function code is not shown here. Just assume that they are available. They're just not shown here. It's not important one of those code. Okay, not important one. So that's why you see here we have this. This is the function prototype for the LED on. You have a function prototype for the LED off. Function prototype for UART config and UART echo. These are serial port functions. Okay, so let's go back to the task. So task 0 is to turn on LED 0, blink LED 0. Task 1 is to blink LED 1. All right, nothing impressive here. It's just running forever. On LED 1, software delay. Off LED 1, software delay, running forever. Okay, nothing special here. Then task 2 is the same. Task 2 is blinking LED 2. Task 2 is blinking LED 2. Okay, all right. Then task 3. Now, this particular program was tested on a board with only 3 LEDs. So unfortunately, task 3 cannot have its LED. So to test this program, task 3, instead of it just sends something to the serial port. UART is a serial port. So task 3, it will just keep sending something to the serial port continuously. Anyway, this is just 4 programs. Now we're going to run these 4 programs one after another, round robin style. How do we do it? All right. How do we do it? So let's go back to the start of the program. Okay. So we have stdio.h because we want to use printf. We have stdio.h because we want to use printf. Where is my printf? Do I have printf here? Ah, yes. You see, there is a printf here. Okay, printf. So we are printing context switching demo one. Blah, blah, blah. Now, let me give you a side story here. Don't use printf. Don't use printf. Don't use printf. Okay, I said 3 times already. Don't use printf. In your assignment 2, you notice there is a printf there, right? You see, printf is part of the standard library. The standard library is supposed to be used on desktop computers, laptop computers, lots of resource. You got lots of memory, then you use the standard libraries. Okay? When you're running on the mouse controller, you shouldn't use standard libraries. You should write the code yourself. Don't use standard libraries. Don't use standard library functions. Write the code yourself. Otherwise, a lot of unpredictable things will happen. Why? Because the standard libraries, right, they use memory in a certain way. If you're writing a very simple program, you use printf, you may not notice the error one. But when your program becomes more complicated, you are dealing with a lot of memory pointers, etc. Right? Then weird things will start to happen. Why? Because printf and all the standard library functions, they use memory in a certain way. Because you don't understand, you're just using the API, you're just using the function. You don't know how those functions deal with memory. So in a microcontroller, when you control everything yourself, you might be doing something conflicting with how the standard library is using memory, and then you will create bugs, and it's very difficult to debug. Because why? You don't understand how the standard library functions are written. So you want to fix it, there are 2 ways. Either you go and understand how the standard library function code is written, or you go and modify the standard library function code, both of which is extremely time consuming. The simpler approach is just to write your own function to send something to the serial port. Don't use printf. Just write your own function to send something to the serial port. Just use the serial port library functions. Don't use printf. Okay? Right. This is only for embedded systems and microcontrollers. If you're programming with a computer, you can use printf. It's made for desktop computing. Okay? Right. Now here, we have this macro. We have this macro, um, hardware 32 rack address. What does this macro do? This macro allow you to access uh, the location pointed by this address. As you can see here, this macro is actually implemented like this. The address that you provide will is unsigned long volatile, is a pointer. So the address that you provide becomes a pointer, and then you go and access wherever this pointer is pointing to. So basically, if you use this macro, you provide an address, you are actually accessing that location. If you use this macro, you are accessing that location. For example, if you type something like this, if let's say you type if you type hardware 32 underscore rack, then you put 0x40000100 equals to 0x ff. So you are actually putting ff into this location. Okay, you see, you are taking the address, making it a pointer, and then you're accessing wherever the pointer is pointing to. Basically, you are accessing this address. So if you do something like this, means you are actually putting this value into the location with this address. Okay, basically, you are doing, basically, you are doing, yeah, wait, okay, basically, you are doing this, pull this a bit, pull down a bit, you are putting 0xff into this address 40000100. Okay, so this is what you're doing. Okay, all right. So let's go back to the code. Okay, so where we are. So okay, that's this one. So we have, these are all function prototypes. Then here I got this function, task init, task init. So this function task init, we got 3 parameters: ID, program counter, and PSP value, right? does the task init do? You see, what does task init do? Task init, you pass it three parameters. You want to initialize the stack of this task, right? You need to initialize the stack of each task. You see, here I got two tasks, task one, task two. Then I got the thread for task one and the thread for task two. You need to initialize the thread for each task, the stack for each. You need to initialize the stack memory for each task or thread. So how do you initialize the stack memory? First, you have to provide the task ID. So the task ID is just a number, 0, 1, 2, 3. If you got 4 tasks, the first task ID is 0 lah. Second task ID is 1. Third task ID is 2. Fourth task, the ID is 3 lah. 0, 1, 2, 3, corresponding to 4 tasks. Then the program counter value, right, is where the task code is located. You need to initialize the stack with the program counter value so that the thread, the task, it can resume execution at the correct place. So you need to give it the program counter value, which is where the thread code is located. And also the PSP value, which is where the stack for this thread is located. Okay, you see here, we have created 4 stacks. Task 0 stack, this is an array. Task 0 stack, task 1 stack, task 2 stack, and task 3 stack. We have created 4 arrays, 4 stacks for each task. Okay, so as you know, the name of the array is actually the address to the start of the array, right? The name of the array is the address to the start of the array. So basically, when you call the task init function, right? You see here, we initialize the 4 tasks. So task init, the first task, we give it a value. The ID is 0. Second one ID is 1. Third one ID is 2. Fourth one ID is 3. And then the second parameter, which is the program counter value. What is the program counter value? You are just giving task 0. You see, task 0 is the name of the function. Now, in C programming, the name of a function is actually the address. It's actually a pointer to where the function code is located in memory, right? The name of a function is actually a pointer pointing to where the function code is sitting in memory. In other words, the address of the function code. The name of a function is actually holding the address of the function code. So you pass the name of the function to task init. You pass the name of the function to task init. So the name of the function, the second parameter, you notice the second parameter, PC value, it will be saved. It will be saved into the stack. So you access the stack and you save it into the stack. Okay, you save it into the stack. The PSP value is the third parameter, right? So what's the third parameter? See, when you initialize the task, the third parameter is actually the name of the stack. The name of the stack is the address, right? The name of the stack is the address where the stack is located in memory. So when you give it the name of the stack, you're actually giving it the address where the stack is located in memory. So you see here, the name is the name of the stack plus the size minus 64. The name plus the size minus 64. Okay, so the name of the stack is starting from the bottom. Let me draw a picture here. The name of the stack. Okay, draw a picture here. Now, you see this is the, let's say task 0 stack. Okay, this is task 0 stack. Now task 0 stack, the task 0 stack is actually a pointer pointing to where this stack is starting. Task 0 stack is actually pointing here. If you add size of task 0 stack, size of task 0 stack will return you with the size in bytes. So if you add the size in bytes, then this arrow will go to the top here already. Then if you minus 64, you minus 64, then you come here. So this will go down 64. Then you'll be pointing here now. So you're pointing here. Why you're pointing here? Because we are assuming that the CPU registers have been loaded in already. Okay, so up here, this 64 bytes is the 16 CPU registers. So this is the 16 CPU registers. So assuming that the CPU registers are all inside already. So your stack pointer is then pointing here now, ready to run. This is how you initialize the stack. So your stack pointer, your stack pointer, oops, not PS, SP. Your stack pointer is pointing here, okay, where the 16 CPU registers are already loaded in, ready to run. So when it is this task turn to run, then you will just load from the stack pointer, load back into the CPU registers. So the 16 CPU register values here will go back into the the actual CPU registers, and then this particular thread can continue execution. Okay, so this is how we initialize. So after we initialize the four tasks already, okay, then this is just to set the priority of PanSV to lowest priority, sysdig to highest priority. Okay, then we have to set the current task to 0 because we want to start with the first task. Set the current task to 0, and then set the stack pointer of the current task to the top. Um, Set your sysdig to every 1 second, every 1 millisecond if you're running on the 48 megahertz clock, right? And then you can start your task 0 already. Start your task 0. Okay, when you call task 0, so what happens is the processor comes here. So task 0 starts running. Okay, task 0 starts running. Run for how long? For what? For 1 millisecond. Why? Because just now you set the sysdig timer to interrupt after 1 millisecond. So task 0 will run for 1 millisecond. After 1 millisecond, wherever it is, your execution will stop because now an interrupt has happened. So the processor will then run the sysdig handler exception. Okay. So then you do a switch current task. What's the current task? 0. So case 0. So next task becomes 1, and you break. You come out here already. Come out of this switch case. Come out here, and then you check: is the current task equals to the next task? No, because current task is 0. Next task is 1, not equals. So if it's not equals, then you need to do context switching. So you trigger a Pendable Supervisor Call exception. This is you set bit 28 of ICSR. You are setting the pending bit of the PanSV exception. Okay, then you return. So when you return, because you triggered PanSV exception already, so when you return from sysdig, you will tail chain. You will continue with PanSV. Okay. So what PanSV does here is, you notice this is in assembly. Why this in assembly? Because we need to move CPU registers. Okay. Why we need to move CPU registers? Because you see, when task 0 was running just now, its CPU registers, its CPU registers is holding its value, right? When the sysdig exception happens, automatically the basic stack frame is saved into task 0 stack. Okay, this what happens when the sysdig exception happens. When the sysdig exception happens, okay. So right now, task 0 is running. Task 0 is running. So this is the task. This is the task 0 stack. So task 0 is running. When the sysdig exception happens, the basic stack frame will be saved into memory. So what is the basic stack frame? XPSR, PC. Okay, sorry, XPSR, PC, LR, R12, uh, R3, R2, R1, R0. So you got these 8 registers. These 8 register values will be saved. So this is your CPU. From your CPU, when you're running task 0, the system tick interrupt happens. So the CPU register values used by task 0 will be saved into task 0 stack, which is this basic stack frame. Then the system handler will run, okay, and it triggers PanSV. So then PanSV runs. And PanSV's job is to switch to the next task, task 1. But if you look at this, have we saved all the registers yet? Not yet. We only have 8 registers saved here. We still need to save R4 to R7, R8 to R11. You still have to manually save this. Right? The automatic register saving mechanism only save these 8 registers. We still need to manually save another 8 registers before we can switch to task 1. So which is what happens here. So the PanSV handler, this code here is to save the manually save R4 to R7, R8 to R11, manually save it into the stack, and then manually load R4 to R7, R8 to R11 of the next task, manually load it, right? Because it's not automatic, you have to manually do that of the next task. Okay, then only resume the next task. Okay, so that's the concept. That's the concept. So um, now try to go through this code first to understand how what I just told you how it works, right? And if you really have difficulty understanding, then you let me know lah. But if you study this, you find it's pretty straightforward the concept. Okay, right. Uh, before we go off, sorry for the delay. Almost 10 minutes past 3. Okay, let me take attendance first. Chu Zhanghing, are you here? Chu Zhanghing, Chu Zhanghing, are you here? Uh, Hong Xuewen, Hong Xuewen, Hong Xuewen, Tan Xinsheng, Tan Xinsheng, Wang Chongyi, Wang Chongyi. Wait, check. Xuewen, Tan Xinsheng, Wang Chongyi. Okay, not Chu Zhanghing. Oh, Tan Xinsheng is here. Tan Xinsheng is here. Uh, Tan Xinsheng, are you here? Tan Xinsheng, Tan Xinsheng, are you here? Okay, maybe he went to washroom or something. Okay, now I'll just take his attendance. Hong Xuewen, Wang Chongyi, and Chu Zhangheng. Here. Okay, never mind. Okay, class, do you have any questions of the materials that we have discussed today? Any questions? Today we talked about uh, Cystic, MPU, SVC, and SV. Do you have any questions so far? Class, everything okay? Right, so everyone else, all okay? No questions? Supervisor call, Pendable supervisor call, Cystic, and MPU. How these support the operating system? Okay. Now, if no problems, please go through this chapter 10 in detail. Please go through these materials or operating system support materials in detail because this chapter puts together everything that you have learned so far. So if you understand this chapter, then you'll be able to integrate all the information that you have learned so far on the processor architecture and also on the RTOS. Okay, right. And if you have any questions, feel free to contact me via WhatsApp or email, right? Okay, so that's all for today. Thanks everyone for coming.